This Explain Everything video is intended as an instructional resource to help teachers to more effectively conduct the lesson as described in the teacher notes in this unit. The same acceptable use policy restrictions apply to this video as they do to the rest of the curricular materials made available by AMTA. Let's review the equilibrium situations we have examined thus far. First was liquid-vapor equilibrium using butane. Here the opposing processes were vaporizing and condensing. Next was solubility equilibrium using calcium hydroxide. Here the opposing processes were dissolving and crystallizing. Both of these processes involved an exchange of particles between the condensed phase, either liquid butane or solid calcium hydroxide, and a dispersed phase, the butane vapor or the calcium hydroxide in solution. Now we're going to examine a case in which the solute iodine is dispersed between two immiscible solvents, water and hexane. One would expect that the nonpolar iodine would dissolve in the nonpolar hexane, but not so well in the polar water. Iodine's low solubility in water can be enhanced by the presence of iodide ion. These two species react to form the triiodide ion, which is readily soluble in water. We start the demonstration by adding drops of iodine and ethanol to a dilute solution of potassium iodide in 3 vials. Vial 1 contains 2 drops of iodine, Vial 2 3 drops of iodine, and Vial 3 9 drops of iodine in the aqueous potassium iodide. Next, a volume of hexane equivalent to the aqueous layer is added to Vial 2. Vial 1 will serve as a color comparison. Vial 2 is shaken to mix the hexane and aqueous layer. When the layers reform, the aqueous layer of Vial 2 is compared to that of Vial 1. Since the color of the aqueous layer in Vial 2 closely matches that of the aqueous layer in Vial 1, we conclude that 2 drops of iodine remained in the aqueous layer and 1 drop moved into the hexane layer. Next, we'll examine what will happen if an equivalent volume of hexane is added to Vial 3. If 1 drop of iodine saturates the hexane layer, then we would expect the intensity of the color in the hexane layer in Vial 3 to be the same as that in Vial 2. An equivalent amount of hexane is added to the 3rd vial. The vial is shaken to mix the layers, allowing some of the iodine to move into the hexane layer. After the layers reform, it is clear that more than 1 drop of the iodine moved into the hexane layer. The question now is, how many drops of iodine remain in the aqueous layer? To answer that question, iodine is added dropwise to Vial 1 until the color of the aqueous layers in Vials 1 and 3 match. Three drops, 4 drops, for a total of 6 drops in Vial 1. Apparently, the iodine partitions in the same 1:2 ratio as it did in Vial 2. Now use the equilibrium game board and 30 chips to model this partition equilibrium. To facilitate discussion, let side A represent the aqueous layer. After you have distributed the 30 chips over A and B space, decide what transfer rules would allow the system to remain in equilibrium. Recall that in the solubility situation, you had one row of chips leave the solid to go into solution, but 3 rows of chips left the solution to crystallize back into the solid. Here the situation is a bit different because the iodine is in solution in both the hexane and aqueous layers.